Hey, this is Marcus, and I'm here to show a new graphical shell for servers and edge devices. Here you see I'm connected to a Raspberry Pi over SSH, and I have this set of apps that I can run. For example, I showed in a recent video this top app. It's a process monitor app, but it has more of a graphical user interface than you'd usually expect over SSH. I also now have a Files app where you can view and preview files for like looking at charts that you generate. There's also now a profiler that generates flame graphs, it's zoomable. And there's a text editor for editing the files on this device. And I'm going to spend a little more time on those apps, but first just let's talk about the fundamentals of how this is working. How do you get graphical user interfaces for a remote device? So I list three options here. First is just our baseline. You just give up and say, I don't want graphical interface. Let's do it all through text. And there, when you run apps, the apps run on the server and they output text. Going a good step above that, you can move to what you could call the remote desktop approach, where the app runs on the server and then the pixels or some description of the visuals get sent across the wire. You can do this in a terminal with X, where you actually get to run a Linux app on your local machine, like on a Mac, where the app is actually running on the Linux device. And this is really cool when you get it set up, but everyone who's used it knows it's quite slow. Another mindset we can bring to the table here is approaching this like a web app, where instead of running the app on the server sends the code to the client runs the app, and from that point forward, the only thing the server is outputting is data. The client is asking the server for updated data, and then it figures out how to display whatever it needs to display. And this is the space that I'm kind of playing in. But I'm not just using existing browsers. I've taken the web browser and pushed it in a few directions, changing its networking to embrace SSH, and I've also created an alternate to the conventional HTML and JavaScript web, where HTML and JavaScript are just an option, but there's another way. So what you're looking at here is essentially a browser. This thing up here is an address bar, where this part is the host name, but instead of being like a domain name on the internet, it's actually a path to a Unix socket on this device, or rather it's a friendly name of it. I'll hover over it to see the messier version of it. A socket is just like a localhost port, except it lives on the file system, so it has different permissions. And of course, being a browser, this does support the HTML and JavaScript web, so that means that there's the whole world of existing web apps that work on this already. For example, here's Jupyter. So here Jupyter is running locally on this Raspberry Pi. It's not even accessible to the local network. Rather, here I'm connecting to this Raspberry Pi through SSH and then locally talking to it via the SSH process. And because it's using a socket rather than a port, it's only accessible to this user, which means I can actually disable all of those security features you might know from Jupyter, where you have to copy and paste a token from the terminal to the browser. So it really just smooths out the process. And if you want to bring your existing web app, because there are so many of them, you can come and do that. You just run the command here. For example, I'll do TensorBoard. So here I have a deep learning project here, and I'll do uv run TensorBoard vector equals runs. I happen to know TensorBoard always uses port 6006, and then we say save. And now we have TensorBoard running, and we can open it. And we did all this without exposing this port to the open internet, and you don't have to think about port forwarding. You just click the link and it goes. So I could have built all of these apps as conventional web apps, including this home screen itself could have been a conventional web app. But I think we can do better and build like actual native apps. So these are web-like apps, but they're truly native. Instead of downloading HTML and JavaScript from a web server, they download an actual compiled binary and load it into a sandbox process. And that compiled code then renders using the underlying operating systems APIs. It calls, in this case, it calls macOS APIs to render an app. So this isn't really even a platform. You could call it like an unplatform. It's intentionally avoiding being a platform. It's passing through the underlying one. This passes through macOS. And I told you at the beginning of this that this is a graphical shell. If I were a business major, I might call it an operating system, but shell is a more accurate term. And what do I mean by that term? Well, first of all, this home screen is where you see your apps and you launch them and you manage them. But there's more to it than that. And I'll go back to the Files app to emphasize this. So this Files app is useful on its own. You can browse around, look at logs and config files, especially on Linux where so many things are text files. You can just like quickly browse through them and see things. But what really makes me call this holistic system a shell is that I can right click a file and open it in another app. And going back, this Files app is not actually aware that there is an app called plaintext. Instead, that same shell that provides the home screen, it provides a notion of file types and openers for file types. So the Files app then asks the shell for apps for a given file type, and the shell says, there's a plaintext app. And when I open it, it's simply a browser navigation, navigating from one socket to another, similar to how a browser navigates from one hostname to another. And importantly, as you saw, the whole thing is pseudo-aware. You can open a file in the plaintext editor running as root, even though the Files app was running as user. And now we're free to edit this. I can go in and like set this IP address. We can also reach it through Peaches. We can access localhost through Peaches. And now I can be goofy and go to Peaches port 6006 and find TensorBoard still waiting for us there. Okay, let's clean that up. So with the remaining time, I just want to demonstrate that there's a lot of low-hanging fruit in this space. You've already seen some, like how the Files app lets you quickly look at Linux's various config files or drag files to and from the machine. I didn't show that, but it works. Or it lets you look at charts generated by a Python script, so you don't have to like sync it locally to view it. I spent a whole other video talking about this top app and how being able to select time windows makes this type of app much more useful. Another app that I found to be immediately useful was this flame graph profiler. So here I'll profile a process that I know is using CPU. It's going to be the backend for that top app, and we'll record. And in a new tab, I'll open top just to intentionally make it use some CPU. So I'm going to change the selection a lot, so it's getting like a lot of probes for different time windows. Okay, I'll close that and stop the recording. And so here you have a flame graph of all of the functions that ran, and you can zoom. You can zoom and find like what's way deep down on this stack. And importantly, you can select different time windows. So that beginning part, when we weren't looking at it, it was just in the background sampling processes. You see the main thing that's running is this Linux read process function. You look at those other times when we were being goofy with the selection time window, and you see there the main thing that was running was this generate and queue frame, build time window time snapshot. A lot of people know how these tools work, but I'm just quickly showing you why it's useful. And these kinds of tools are kind of table stakes on Windows and Mac OS. And you can kind of get them for Linux, but it usually involves running some command line tools, and then you sync it locally, and then you can't zoom it. So these things, you can't really see what these functions are. You have to regenerate it, and you don't get like the selection of like individual time windows. And now without very much work, I have all of that because all the pieces are there. The last app I'll show is this one called Firehose, which is a log of various events on your computer. I call it Firehose because you very quickly accumulate tens and hundreds of thousands of events, so it's like drinking from the fire hose. This tool is definitely inspired by Process Monitor, or Procmon on Windows, which is a great tool. So here's what it looks like to use this. So it's getting tons and tons and tons of events. This big timeline is building up, showing a process tree of everything that's running. And we can pause it and just inspect some of what's happened here. So this is pretty useful to navigate using this process tree. The other really useful thing is filters. When you have these tens of thousands of events, you always are very quickly needing to filter down. And very much like Process Monitor, Procmon on Windows, this filtering UI is a pretty central part of it. I'll go down and just look at what this outer root bridge is doing. Okay, it's talking to pipes, you can see it's looking at this allow list. I haven't told you about that, but the browser can only connect to certain sockets that it's allowed to. That's a security thing because some sockets don't expect browsers to connect to them. And you see it's looking at these pipes. This is where I can show you where filtering is useful. I'm going to right click this and I'm going to say include this pipe so we can see who it's talking to. And you see what's happening here is this outer root bridge, which is my process, is reading this pipe, where meanwhile this SSH process is writing to it. So that's how these two are communicating with each other. So this is how this app was actually talking to the remote machine. You're seeing that through these pipe messages right here. A tool like this sometimes really saves the day. I don't have examples with this specific one because I just built it, but I can go back to, I'll bring this screenshot in. So back a long time ago when I worked at Microsoft on the team that was trying to rescue Internet Explorer, we had this bug with icons disappearing randomly occasionally, and it was perplexing us. Nobody had tracked it down until I managed to capture it under Process Monitor, a tool that's very much like what I've been showing you here. And in one screen, we got the smoking gun of this race between iExplore, which is IE, and Explorer, which were both racing to look at this file, and they would collide with each other and give up, and then you would lose an icon. Once we had this traced, we were able to quickly fix the bug. And I was such a nerd back then, I made this my Facebook header photo, which is why I still have this image. Tools like this have existed on Windows and macOS for a really long time. And in some sense, they exist on Linux as well, but not in a form that I find accessible. So these last two apps, the profiling app, the tracing app, I spent essentially just a few hours building them with heavy assistance from AI. So my point here isn't that you should use these apps, though, I mean, I recommend it, but you don't have to. It's that if we can get ourselves into a place where we have these first-class graphical user interface apps, then there's suddenly tons of low-hanging fruit. So I do hope that you go download Outer Loop and use all of this if you're a Mac user. There's currently only a Mac version. But my real goal here is to convince you that something like this is a good idea. Servers should have an external outer operating system or shell. The browser or something similar is almost inevitably part of this because it's the place for safe external apps. I think the SSH client and the browser can really come together into something interesting.